In this session, Youngjin Kim overviewed his team's approach to reducing the area and energy overhead of in-memory computing techniques. According to Kim, in-memory computing removes the need to transfer data stored in memory to computing units, while also providing a more energy-efficient way to perform dynamic neural network computations. The main problem with in-memory computing circuits, however, is that there is significant energy and area overhead because of the digital to analog and analog to digital conversions needed to translate between digital and analog signals. Kim claims that these problems can be resolved by the use of quantization and binary neural network techniques. The software-hardware co-design approach presented in his session employs the use of an algorithm called bit split to process quantized input data through a neural network and an in-memory computing circuit called Mosaic. Using these techniques in tandem, Kim and his team were able to reduce the energy of their in-memory computing circuit by about 90 times and the area of the circuit by about 34 times when compared to popular prime-like in-memory computing techniques. This paper is interesting to me as a first-year PhD student because it sufficiently outlines popular in-memory computing approaches for me to research during my studies, and it highlights the main issues that arise when attempting to implement this technology. From this paper, now have a better understanding of quantization, binary neural networks, and how in-memory computing can be improved in the future. This paper may be especially useful to reference in my future research, which seeks to create 3D neuromorphic integrated circuits by providing a means of further reducing area and power consumption in these designs. Perhaps future research on this topic can explore how the presented approach performs when used for classification of sounds and other types of data.